ME204, Linear Impulse and Momentum of Particles. A ball that is flying through the air at some velocity has momentum associated with it. When it hits a wall, there's an impulse that occurs that changes the direction and the velocity of the ball. If I have a larger mass, say a car or a truck, that's traveling at the same velocity, it also has momentum, but because the mass is larger, the momentum is greater. It also creates an impulse when it hits the wall, but that impulse is going to be felt differently with a larger mass than it would with a small mass like a ball. Let's look at where impulse and momentum come from. If we start with our equation of motion, force equals mass times acceleration, knowing that acceleration is the derivative of the velocity with respect to time, we can substitute that into our equation to get that the force is equal to the mass times the derivative of the velocity with respect to time. Rearranging this equation gives us force dt is equal to mass dv. If we integrate both sides, on the left side integrating from our initial time to our final time, and on the right side from our initial velocity to our final velocity, if the force is constant, then we get a force times a change in time, our final time minus our initial time, is equal to our final momentum, mass times the velocity 2, minus our initial momentum, mass times velocity 1. Rearranging this gives us our initial momentum plus an impulse, a force times a change in time, is equal to our final momentum. It's helpful to understand the differences between kinetic energy and momentum and how we solve these types of problems. When we're looking at kinetic energy, we use 1/2 mass times the velocity squared. This is a scalar quantity. There's no such thing as negative when we're dealing with kinetic energy, and the direction really doesn't matter. For momentum, however, it's a mass times a velocity vector. This is a vector quantity. Direction does matter when we're dealing with momentum. For work versus impulse, work was defined as a force times a change in position. Again, this is a scalar quantity. The force and the change in position have to be in the same line of action. And negative work means that the force is in opposite direction of the displacement. An impulse, on the other hand, is a force vector times a change in time. Again, it's a vector quantity. The impulse vector is in the same direction as the force vector. Now let's compare work and energy versus impulse and momentum. When we were dealing with work and energy, we said that our initial energy, plus or minus the work, equals our final energy. Or, work is equal to our final energy minus our initial energy, which can be stated as work causes a change in energy. For impulse and momentum, we have our initial momentum plus an impulse equals our final momentum. And again, these are vector quantities. Or we can rewrite this to say that an impulse is equal to our final momentum minus our initial momentum. Another way to say this is that impulse causes a change in momentum. But again, because these are vector quantities, we have to break these down into x, y, and z components to solve the problem. So how do we know which approach should be used when we're trying to solve a problem? Should we use work and energy or impulse and momentum? Well, we know that energy deals with an initial energy state, plus or minus work, equals a final energy state. And impulse and momentum is initial momentum plus an impulse equals final momentum. So how do we know which approach we should use? Well, work in our energy equation deals with distance. Work is equal to a force times a change in position. Impulse, on the other hand, deals with time. Impulse is a force vector times a change in time. So if we read the problem and look at what it's asking for, we can get a better understanding of which approach should be used, whether we should use work and energy or impulse and momentum. For example, if I have a 20 kilogram rock that's being pulled by a 100 Newton force, as shown in this picture, how fast will the rock be traveling after it has moved 4 meters? Because it's dealing with a change in position after it's moved 4 meters, we would probably want to solve this problem using work and energy. On the other hand, what if we had a similar problem, 20 kilogram rock being pulled by a 100 Newton force as shown, and we want to know how fast the rock will be traveling after 10 seconds. In this case, we're dealing with a problem that's moving for a specific period of time, 10 seconds. If we have a change in time, then it's probably best that we use impulse and momentum to solve this type of problem. Here's an example dealing with impulse. If we have a 3 kilogram rubber mallet that's moving at a velocity of 10 meters per second just before striking the stake, when it strikes the stake, there's an impulse that occurs and the hammer's momentum reduces to 0. We could write our momentum equation, our initial momentum plus our impulse, a force times the change in time, is equal to our final momentum. Or our impulse is equal to the change in momentum. Well, we know that when the rubber mallet strikes the stake, the momentum stops. It reduces the momentum to 0. So we can cancel that term out. Our initial momentum is simply the mass times the initial velocity, or 3 kilograms times 10 meters per second, which is 30. So our impulse, our force times the change in time, is equal to negative 30 kilograms meters per second. This is our impulse. If we keep the impulse the same at 30, and we know that the time that the rubber mallet strikes the stake is equal to 0.1 seconds, then we can calculate the force in this example. In this case, it would be 300 newtons. What happens if the time of impact is reduced? If the time of impact goes down, then the force of the impact has to increase in order to keep the same impulse. What if we had a wooden mallet instead of a rubber mallet? Now we've got a material that's a little bit more stiff than the rubber mallet. So when it strikes the stake, that time of impact is shorter than it would be with a rubber mallet. If our impulse stays at 30 and the time decreases to 0.01 seconds, then our force increases to 3,000 newtons. Now what if we had a sledgehammer, a steel sledgehammer? In this case, when it strikes the stake, now there's not very much give at all. Our impulse is the same. The time of impact decreases even further, and if our time of impact were 0.001 seconds, then the force of that sledgehammer hitting the stake becomes 30,000 newtons. Here's another example related to impulse and momentum. Your body is seatbelted into a car traveling 75 miles an hour. In a head-on collision, the seatbelt creates an impulse on your body that causes your body's momentum to reduce to 0. What's the purpose of the crumple zone in the car? Notice in this truck that when the truck hits the wall, the front of the truck crumples. If you're not wearing a seatbelt, will this crumple zone affect the force that your body experiences? Remember that large forces cause damage to the body. Well, if we look at our impulse and momentum equation, our initial momentum plus our impulse is equal to our final momentum. If we come to a complete stop, again, what happens if the time of impact is reduced? Well, the force of the impact has to increase. So the more of a crumple zone that we have, the longer the time of impact is, and the force decreases. So what if we're not strapped in tight into our seatbelt? Then our body will not be slowing down while the car is crumpling. Our body keeps the momentum that it has until it strikes another object. Your body will be stopped in a much shorter amount of time, which causes the forces acting on your body to be astronomical. So it's very beneficial to wear your seatbelt and trust the design of the vehicle that crumple zone is going to extend the time of impact, reducing the force that's exerted on the body during the slowing of the momentum. So for impulse and momentum of a particle, linear momentum or translational momentum is a mass times a velocity vector. If I have a mass that's 1 kilogram that's traveling at 2 meters per second in the x direction, then my momentum, the mass times the velocity vector, is equal to 1 kilogram times 2 meters per second in the I direction, which is equal to 2 kilograms meters per second in the I direction. For a linear impulse, we have a force vector times a change in time. Again, if I have an object that's acted on by a 2 Newton force for 5 seconds, then I can calculate the linear impulse as the force vector times the change in time. Or in this case, 2 newtons in the I direction times 5 seconds, which is equal to 10 Newton seconds in the I direction. Newtons are kilograms meters per second squared, so we have 10 kilograms meters per second squared times seconds in the I direction, or 10 kilogram meters per second in the I direction. Our next topic will be particle kinetics using impulse, linear momentum, and conservation of linear momentum.